Ladies and gentlemen, our next speaker is a programmer at Plastic. He's currently working on Bound, which was already discussed yesterday. And during his almost 7-year experience in game development, he was responsible for various gameplay, physics, audio and network subsystems in productions such as Datura on PS3, Godzilla Benchmark for PC, and he has also programmed visual effect for miscellaneous interactive shows. Please welcome to the stage Mr. Andrzej Uszakow.
Hi, my name is Andrzej Uszakow. I'm one of 4.5 programmers at Plastic, and I will talk about physically based effects. Plastic, we are a small team based in Łódź with some deep demo scene roots. And we have also some people in Santa Monica and Ukraine we work with. And for now, we have released Lingering Shadows for PS3 platform. It's an interactive demo. Datura also for PS3 platform. It's a mysterious adventure game. And Godzilla, it's a benchmark for PC. And nowadays we are working on Bound for PS4 platform. It's a story-based game with 3D platformer mechanics, and we are trying to combine game with a node game. And also there are some demo scene influence. Like where I have some pictures. Let's back in time to Datura and Godzilla. In that productions, most of our physically based stuff was made using physics middleware. And as we know, all of physics middlewares have its own specific API, feature set, performance and stability. And during production and prototyping, we had to adapt our ideas to those limitations. And often we struggled with some strange results and stability and performance issues. And in Bound, as we can see, we have a lot of custom, simple, physically based effects, and we limited usage of physics middleware mostly to word collision and some character controller simulation. And we treat each of our effects individually. It's kind of, every effect is kind of small self-contained physics system. And to do that, we use position-based dynamics. It's easy, simple to implement a technique that allows us to much more faster prototyping and development of our effects. And in this presentation, I'm gonna cover basic algorithm of position-based dynamics, and I will discuss some basic constraints as well, and then I will show some examples, effects created using PBD. Okay, position-based dynamics is kind of particle system, and basic particle in such system has position, predicted position, velocity and mass, but instead of using mass, we are using inverse of mass because of kinematic particles. And imagine a situation where you're trying to attach some particle to word space. And in such case, the particle has to have infinite mass. But using infinity in our calculation is a bad idea. But if you take inverse of mass, then 1 over infinity is just 0. And it's a solution to this problem. And of course, each particle can be constrained, and depends on what kind of constraint you will use in simulation. You can simulate rigid body, fluid, cloth, hairs, fur, ropes, whatever you want. And basic PBD loop. Before simulation start, we have to initialize data with some values, position, velocity, and inverse of mass, and some constraints are pre-computing some internal data. And first step, for each particle we compute velocity using explicit Euler formula, where Fx is an external vector, external force vector. In most cases it's just gravity. Then we dump velocities. You can dump velocity in very simple way, just you can scale velocity by some value from 0 to 1, but you can also do some more sophisticated method, like described in position-based dynamic papers. I will give some links to those papers at the end of presentation. Next, we predict position of particle like in unconstrained motion, again using explicit Euler formula. After that, we generate collision constraint. When the particle overlaps with some obstacle, we generate the penetration constraint that moves a particle along collision normal to remove this overlap. And now, the most important part of our loop is we are projecting constraints, and inside this loop, every constraint is trying to correct particle position to satisfy some internal conditions, and we are doing this in loop. Well, in most cases, for iteration is sufficient. After that, we recompute velocity of particle. We are using corrected predicted position and position from beginning of our loop. And of course, we have to handle situation where delta time is 0. Next step, velocity update. It's actually an additional step. We are updating velocity due to collision restitution or friction. And this is the end. Now I'm gonna talk some basic constraint, and the most common and the simplest constraint is distance constraint. This constraint is trying to keep proper distance between two particles. Particles are displaced along constraint direction. It's a normalized vector between these particles. And of course, delta positions are proportional to particle's mass. Next, basic is a bending constraint. Here we have 4 particles forming 2 triangles with one common edge, and before simulation we need to compute our reference angle. To do that, we compute normal vectors of those triangles, and angle between normal vectors is our reference angle, and during simulation we recompute this angle, our current angle, and here we have 2 options. We can treat this like equality constraint. In that case, this constraint is trying to keep reference angle between triangles, or we can treat it like inequality constraint. In such case, for example, constraint is projected only when our current angle is less than reference angle. Of course, there is also another implementation of bending constraint involving only 3 particles. We don't need 2 triangles. Other useful constraint used in our effects is long-range attachment constraint used for simulating inextensible cloth. In this constraint, every particle can be attached to some point. Usually is a kinematic particle. Before simulation start, we pre-compute distance between attachment and particle, and during simulation, when current distance between particle and attachment is less than reference distance, the particle can move freely. But if the distance is greater, we will project back particle to satisfy distance. And follow the leader constraint is used to simulate inextensible hair or ropes. The good thing with this constraint is we need only one solver iteration to ensure inextensibility, but this technique produces uneven mass distribution in our system, and we need additional velocity correction. If I remember correctly, it is 2.7 point of our algorithm. Okay, let's go to some examples. And the most common example of usage of position-based dynamics is cloth simulation. Here we have distance constraint and bending constraint to keep overall structure of cloth, and additionally long-range attachment constraints to stiffly attach the skirt to the character. Thanks to that, the skirt do not float on character when she is moving. I have some video. Also, there is some collision constraint between cloth and the character. Next, ribbons. These red ribbons, each of red ribbon is it's a kind of rope where first particle is attached to player hand. Again, distance and bending constraint for overall structure of ribbon. And in this case, we are using follow the leader constraint. And together with quite high velocity damping, it produces nice trail-like movement. And here we have also blue ribbons, are similar to red ones, but instead using of follow the leader constraint, we use long-range attachment constraint, because for this case it's more suitable. But the blue ribbons are moving around character on the sphere surface, and long-range attachment constraint is better for this case. Hair. Hair, this is abstract hair. There are some kind of convex shapes built with particles connected with distance constraints, and every of these convex shapes is attached to head with long-range attachment constraint to prevent floating hair on character head. It's quite simple. Aerial silk. Aerial silk is a rope attached at one end toward space, and of course distance and bending and long range attachment constraint to keep rope-like behavior, and bounding tube constraint is actually collision constraint. This constraint is keeping aerial silk inside virtual tube. It's very helpful when you do some gameplay mechanics, and also it prevents too much swinging on rope. And of course additional attachments when character jumps on silk. Grass. The grass is an example of effect using only distance constraint, and each blade of grass is created with different angle between surface, and of course grass is a chain of particles connected with distance constraint, and vector between last particle and first particle, it's actually gravity vector for grass. Gravity vector in this case is individual for each blade, and when you apply quite strong gravity and you have particles connected with distance constraint and add some noise to particles, we made grass with that technique. Have video. You can see also collision constraint in action. Monster shards. In this effect, there is no constraint at all, only simple dynamics, and these blue boxes are spawned on character surface in place of skinned vertices with 0 scale, and then each of these boxes grows up, and when it's big enough, is detached from surface and fly away. Quite simple and fast effect. Queen shards are very similar to monster shards. The difference, of course, is shape and spawning points, of course. And there is also applied some noise to velocity to much more rich movement. This is a screenshot from different perspective and video. Queen's skirt, this is made from boxes and placed in helix-like path, connected with themselves with distance constraint. Additionally, long-range attachment constraint to attach stiffly attached to character, and additionally there is some kind of spine from particles inside the skirt, and every of these outside boxes is connected to spine with distance constraint. Thanks to that, the skirt do not squeeze when she's moving. And of course, this skirt is rotating constantly. And those red fringes, it's actually the same piece of code like Prince's hair, but with more segments and some noise. Tentacles. Each of these green tentacles is a chain of particles connected with distance constraint, and also there is a bending constraint, and it's actually hack on position-based dynamics, because we constantly violating bending constraint, we are preventing to converge to proper solution of this constraint, and together with quite high velocity damping, it produces tentacle-like slamming movement of tentacles, like this. Thanks to high stability of position-based dynamics, those tentacles doesn't explode. Tentacles in different perspective. So, position-based dynamics is simple, very easy to implement, robust and fast technique to do some visual effects. And you can write at your own some physics system based on PBD algorithm, and I encourage you to experiment with this method. Any questions?
I was wondering if you could give us some numbers about how many particles do you have at the same time in like a game scene, and not a fabricated like test case, just in game. How many particles at the same time can you have? And also, how do you run the solver? Is it CPU code or is it a compute shader? And if it's a compute shader, is it synchronous or asynchronous compute?
The number of particles it depends, of course, of effect. In queen shards or monster shards, there are approximately 10,000 of particles with, I don't know, 50 to 10 microseconds simulating on CPU. Can you repeat other questions?
Yeah, I was asking if it's run on CPU or on the GPU in some way.
Every code of this example is running on CPU side, and the cloth is running asynchronously. we kick task at beginning of our engine loop, and we waiting later when we need some results from simulation.
Yeah, hi. Are you using any kind of multi-threading solver for your particles and for your constraints, or whenever you start solving all the constraints for the cloud, for example, you are using only one thread to do the job?
It depends on effect. In case of cloth, it depends of internal solver of constraint. You can use Gauss-Seidel constraint, and in that case you have to run on single thread, or you can use Jacobi solver. Then you can run constraint solver in more task, but this kind of solver will converge slower. You need more solver iteration to get.
In this game in Bound, you are using basically Gauss-Seidel solver, yeah? On
yes,
one thread.
But in case of grass, for example, each of blade of grass can be processed in separate task. Mm-hmm. They are independent.
Yeah, great. Thank you.
How many steps do you make each frame? Is it one step per frame, or do you have a more physics step each frame?
Again, it depends on effect. Some effects will require fixed step, and then there is, for example, 2 steps per engine frame, or not. You can just do one step per engine frame.
I have a question about counting the constraints for your effects. Do you have in your engine some kind of loading for those kind of effects? For example, the effects that are really far away, are they counted not as many times as those effects, for example, on the Princess or on the Queen?
You asking about some kind of LOD system?
Yes, yes.
Yes, of course. We are not simulating effects that are too far from character. It's quite straightforward.
Okay, thanks.
Would you recommend using this technique for fluid simulation? Like a lot of water, wouldn't it break? I mean, like performance-wise?
You have to check at your own, because it depends what do you want to achieve. It's personally, I didn't do some fluid simulation by this technique.
Okay, thanks.
Another question I have, I understand that when you have the constraints of distance, for instance, that's a constraint between like 2 different particles, right? So do you use for any of the effects, do you use any supporting data structures to accelerate the lookup of data between particles, or just to accelerate the computation, or is it just that the data sets are small enough not to require anything of that kind?
For example, in cloth simulation, some of particles are kinematic, and I don't need to, for example, do collision between those particles, and I create additional index of those particles that needs to be processed with collision constraint, for example.
Okay, so no octrees or anything with that kind of complexity?
No.
Okay, thanks.
Oh yeah.
Hi, good stuff. I have a question about the setup. So do you have any kind of editor for doing different kinds of trails and so on, or is it mostly you doing that from code?
In most cases, I do it from code, but in case of cloth, the cloth is modeled in tool. Then I color some vertices that have to be attached to player, and that's all.
Okay, thanks.
I have a question about the distance constraint. Maybe I haven't heard that, but when you counting the distance between the particles, how are you finding the neighbors of the particle that you have to count the distance? Because you said you have the constraint of the distance and the long distance constraint, right? Mm-hmm. How do you recognize if the particles are neighbors? So you have to count that distance constraint, and when the third particle is too far away to count the distance constraint, and you have to count the long distance constraint.
Before simulation start, I have set of distance constraint in system that I have to process. I do not.
So you do not choose the neighbors on the right time?
No.
Okay.
No.
Okay, I have a simple question about basically skinning those meshes, because as far as I understand, those particles are not like straightforwardly vertices of meshes, just pieces of simulation. So you're basically skinning, moving the meshes based on like two nearest and weight average of those, or is there some more sophisticated stuff going on with skinning?
In my effects, I don't use skinning.
So basically, all the particles are mapped to vertices of those meshes, or how does it?
Character mesh and effect mesh are separate meshes.
Okay, thanks.
Anyone else? We still have time.
Thank you.
Thank you very much.